This is Geometry, Unit 9, Day 4. We're talking about standard position. When we begin coordinate proofs, we'll need to be able to place a figure in the coordinate plane in standard position. Or we could also say in quadrant 1. This means that we will want to place one coordinate at the origin, and we'll want to try to minimize the variables. So instead of using numbers, we're going to use variables to represent the coordinates of our polygons. So for example, with a square, to be in standard position, we need a point at the origin. We need a point on the x-axis. Because a square has a 90-degree angle, we'll place a 90-degree angle here at the origin, which would come up the y-axis. And since it's a square, will be 90 degrees up this side at the same height as our other point, so we can produce the square. So now, since we have the square, we're going to look for coordinates to represent using variables. So of course the origin is going to be 0, 0. We're going to use an A to represent the distance it takes from the origin off to the side for the x-axis. Typically the x-axis will always have an A value there. Now, because it's a square, we know that the distance of each side has to be the same. So the distance along the y-axis has to also be that same value. So it's going to be 0 right and left and A up. That's going to make this fourth point A over for x and A for the y. A for the x-coordinate and A for the y-coordinate. Now we should be able to take those coordinates and prove different parts for a square. For example, diagonals are congruent, diagonals are perpendicular, diagonals bisect at the midpoint, sides are congruent, some sides are parallel, slope of 0, things like that. And if it works for the variables, then it should work for all squares. We're going to try a rectangle. We'll put the short side on the x-axis, put the long side on the y-axis. No specific reason. We'll just try and put a limitation to what we're talking about. So with a rectangle, we know it's 90 degrees, so it has to be straight up. So our first coordinate here will be A0. Of course, the origin is 0, 0. The value along the y-axis. Now we have to decide, does this coordinate have to be related to the other side of the rectangle? For a rectangle, it doesn't have to be the same length, so it can be a different letter. Remember that 0 has to be the x-coordinate if it's on the y-axis, and then some distance up. It can be any distance. We'll call it the letter B. So our fourth point is going to be over the A and up B. Next we'll talk about an isosceles triangle. We'll put a point at the origin, a point along the x-axis. Now, for us to construct an isosceles triangle, we'll need to find the midpoint. And then we'll go straight up from that. You go up any amount you need to. So, one thing we've learned in the past is if a point is on the perpendicular bisector, then it is equidistant to the endpoints of the segment. Equidistant means essentially it's equal in distance to the endpoints. Equidistant. Then it's equidistant to the endpoints of that segment. So, when we draw down perpendicular straight down, we know that that's going to be considered like a height, and this is going to be the midpoint. That's going to help us identify what our coordinates are of that top point. Of course, we have 0, 0. This one's going to be, we typically would call it A0, but since we know that this side is going to be broken into two congruent parts, we're going to call that 2A. That'll just make dividing it in half a little bit easier. In other words, this distance here is A for the other side to make a total of 2A. So it's A over and an unknown amount of distance up. It doesn't have to be up the same distance. For it to be an isosceles triangle, if a point is on the perpendicular bisector, anywhere along that perpendicular bisector, not a specific location, then it is equal distance to the endpoints. So these legs of the isosceles trapezoid, or isosceles triangle, will be congruent. Equilateral triangle. Equilateral triangle implies that all the sides are the same. So here, and if we want the other two sides to be the same, and even the same to each other, then they have to be again on the perpendicular bisector. But this time it has to be a certain distance. If I would go too short or too far, then it would no longer be an isosceles triangle. So of course we're going to label this 2A, so we're sure to know right where this midpoint is located. That's a distance of A. Now remember that an equilateral triangle is also equiangular. So that means that all the angles of the triangle are going to be 60 degrees. So if we look at just one side of these congruent triangles, we're going to have a 30, 60, 90 triangle. So if we have 2A along one side of our equilateral triangle, we know all the sides are 2A. So 2A is the hypotenuse of this right triangle. We've learned from the past that the hypotenuse equals the short leg times 2. So for us to figure out what the short leg is, we would take 2A and divide that by 2. So we'll have an A. The long leg is going to be the short leg times the square root of 3. So if we take the short leg, which is A, times it to the root 3, that would be A root 3. And that's going to be our height. So now we know what the y coordinate is on the way up. We know what the x coordinate is on the way over. So A comma a root 3. That's going to be true about any isosceles triangle. A scalene triangle. A scalene triangle is a triangle where each of the sides is a different length. And for that to happen, we'll use our coordinates. We have 0, 0. Looks like I forgot 0, 0 over here. 0, 0 for the origin, A0. I'm looking at this and I notice that this point does not have to be right at the center line. So there's no need to have 2A. You could do it if you want, it's not a big deal, but A comma 0 is sufficient. Now the distance that it takes to come over to get to that point, there's nothing specific about it. It could have been anywhere. So we'll call that distance something different called B. And the distance up, there was nothing magical about that. It didn't have to be twice an amount or half an amount or anything. So it could be any spot up or over. So that would be our equilateral triangle. Scalene triangle. Equilateral triangle we had done over here, and that was a little bit more complicated. Isosceles triangle. An isosceles trapezoid. Isosceles trapezoid is a trapezoid with two legs that are the same length. So we'll have one parallel side. We'll pick another point. Again, this distance over here can be any amount. This distance up can be any amount. But when we pick this location, the next point, the final point, it has to be up the same amount as this one, and then it has to go over the same amount as that one. That would give us two legs that are the same length. That would give us two triangles kind of out here on the side that are the same measurements. So this distance, which we'll call B, and the distance up we'll call C. Over is B, so this distance here is B. The distance up, of course, is C. So this little bit here is B. So we're going to go all the way out to A, and then we're going to have to back up this distance of B. So this coordinate is A minus B, comma C. That's a bit more complicated than even the equilateral triangle. Look at what we did. We know that A0 is going to be out here to the edge. 0, 0 is, of course, the origin. So once we knew that A0 was out to this point, then we had to back up this distance that was equal to this one. So we went over an A minus B, then up C. This last one, place a rectangle in a coordinate plane so its vertical sides has a length A and its horizontal side has a length of 2A. Its vertical has a length of A, so vertical is up and down, and that's going to be 0, comma A. That is the vertical having a length of A. The horizontal having a length of 2A. So that means that the final point would have to have the A value, or the X coordinate, and the Y coordinate of these 2 points. And of course, this one at the origin is 0, 0.